Welcome back to 15-Minute Math. So this is the second part of a video on the second derivative test. So the first part of the video, we kind of went over conceptually what the second derivative tells us. We got into one example running through the second derivative test, but we really didn't do a lot of examples. So this video, I hope to just do a few examples, run through the second derivative test, and hopefully you can kind of get a feel for how the process works. So we're going to start with this function that you see on the screen here. It's a quartic function. It's another polynomial. If you did watch the first video already, we did a cubic, so we've already done a polynomial, but we'll do another polynomial. I think those are good starting functions for a lot of these calculus tools and concepts. So first thing we want to do is, even though it's the second derivative test, we're going to go ahead and take the first derivative. I guess you can't really get to the second derivative without taking the first derivative anyway. So let's go ahead and do this. So this is going to be x cubed. Oh my gosh. It's going to be 4x cubed. This guy doesn't even know how to use the power rule. Minus 4x. That seems to be the derivative. Now I'm going to double check myself, make sure. Yep, that seems right. And we want to know the critical numbers, or the critical points. So let's go ahead and factor out 4x. Leaves us with x squared minus 4. I'm sorry, x squared minus 1. We factored out the 4. Let's see here. So x equals 0 is going to make this thing go to 0. X equals plus or minus 1 is going to make this thing go to 0. So those are our critical points. Let's go ahead and do the second derivative and find where possible points of inflection may be. And so we'll do the derivative again. That's going to give me 12x squared minus 4. Set that equal to 0. And we'll factor out a 4, and we're going to get 3x squared minus 1. So if we set this factor equal, first of all, notice that this expression will only be 0 if this factor equals 0. So we'll set this factor equal to 0, which means x squared is going to equal 1/3, which means x is going to be plus or minus the root of 1/3, which is root 3 over 3 if you're into that sort of thing. So remember, what we want to do is we want to test to see if these are inflection points, because just because we find that this is where the second derivative equals 0, that does not necessarily mean these are inflection points. Much in the same way that even though we get critical points, that does not necessarily mean those are all going to be extreme values. They're not all going to be minimums or maximums. Not necessarily anyway. Like, remember, like, say we had let's do a cubic function here. Just like the parent cubic. Like, we would get a critical point right there. But that's not a minimum or maximum, because we don't go from increasing to decreasing, or from decreasing to increasing. It's just increasing, and then momentarily the derivative becomes 0. And inflection points can be much in the same way, where the second derivative can just momentarily go to 0, and it can go from positive to positive or negative to negative. So remember, we need to check to see if the second derivative changes its sign, if it goes from positive to negative or whatever. That's going to tell us if these are actually inflection points or not. So kind of like what we do with the first derivative test, we'll just test some numbers that fall in these intervals. So notice that this is going to divide the number line up into negative infinity to negative root 1/3, negative root 1/3 to positive root 1/3, and then anything above the positive root of 1/3. So let's go ahead and let's test something in that first interval. So the square root of 1/3, I think just doing -1 would be fine. And remember, we don't really care what the value is. We just care what the sign is. So I think I'm just going to look at it right there. If I put in -1, well, if I square it, it's going to be +1, so I'm going to get a positive answer out of that, which means we're going to be concave up on that region. So from negative infinity to negative root 3 over 3 is concave up. And remember, the little mnemonic to remember that is, if you have a plus sign, happy guy. Now let's test something in the region between my two possible inflection points. maybe say 0, right? If we're going from negative to positive, 0's got to be in between. And it's really easy to see if we plug in 0, we're going to get a negative number. So that tells me we're going to be concave down from negative root 3 over 3 to positive root 3 over 3. And we have kind of a similar thing there. If it's negative, you kind of have that sad guy. So concave down. So that the negative root 3 over 3 is in fact an inflection point because we go from concave up to concave down. Now let's just test maybe the positive one. And actually, because of this square, positive 1 is going to turn out to be the same as negative 1. It's going to be positive. So from from positive root 3 over 3 to infinity, we are concave up again. So we do have inflection points. Both of them are inflection points because you switch your concavity every time. So now all we need to really do is kind of look and see, okay, well, negative 1 falls in this region, which is concave up. Remember, if we're concave up, that implies a minimum, right? If the critical point lies in a graph that looks like this, that critical point's got to lie at a minimum. So and I guess we can go ahead and jump to the chase. Positive 1's the same way. So we have relative minimums at x equals plus minus 1. And by the opposite logic, you know, if your graph looks like this, you have a critical point, it's got to lie at a maximum. So it's going to be a relative max at x equals 0. So there we go. Second derivative test in action on a polynomial. So let's do maybe something that's not a polynomial. So we're going to have, and we're going to do the same thing. So I'm not going to write out the full set of instructions. We're going to find all the minimums and maximums and all of that for the cosine of 2x minus x. Get a trig function in there. So like before, we're going to go ahead and we'll take the first derivative. So if I take the first derivative here, it's going to be, remember the derivative of cosine's negative sign. And because of chain rule, I need to take the derivative in here, which is going to be times 2. And then the derivative of negative x is just going to be negative 1. Let's go ahead and find our critical points. And so we'll set this equal to 0, and we'll get negative 2 sine 2x minus 1, which means the sine of 2x needs to equal a negative half. Let's see here. Draw a little circle. Zoop. I like how it auto corrects my circles. Negative 1/2. That's going to be on the bottom part of the circle. And if the short side, that's the short side of a 30, 60, 90, 1/2 is. Which means we must be looking at a 30-degree reference. So, yeah, our triangles kind of, those are bad triangles, but they kind of look like that. And this angle in here is a 30-degree. So what would that be? 210 degrees or 7 pi over 6. So we'll either have 7 pi over 6 or 11 pi over 6. But remember, that doesn't equal the thing that we want. That equals 2 times the thing that we want. And so actually the two angles that satisfy our equation is 7 pi over 12 or 11 pi over 12. As long as we're staying between 0 and 2 pi, right? Obviously, you know, we could add 2 pi to either of those and get the same values. So let's go ahead and do the second derivative. Remember, those are possible extreme values. And now let's find possible inflection points. So we'll do the second derivative, which is the derivative of the derivative. And so I'm going to get negative cosine of 2x. But I need to multiply by 2 because chain rule. But I also had a factor of 2 already there. So in fact, this is going to be times 4. And the negative 1 just goes away. You know, constants drop off when you take the derivative. So actually, second derivative is a little bit nicer than the first derivative. So we need to find when does negative 4 cosine of 2x equals 0. Thinking about my circle here. Well, the cosine is equal to 0 at the top and bottom of the circle. Okay, so that would be pi over 2 and 3 pi over 2. But remember, again, that's really not the angles we want. That's 2 times the angles that we want. And so pi over 4 and 3 pi over 4 are actually the 2 values that we want. And those are the possible inflection points. So as we've done before, now what we ought to do is we need to pick a number that falls kind of in these regions and test where the sign of the second derivative in those intervals. So I need to look from 0 to pi over 4, from pi over 4 to 3 pi over 4, and then from 3 pi over 4 to 2 pi. And so let's see here. There's really not a great, I guess pi over 6 is a good one. So let's try f prime of pi over 6. And the reason I picked pi over 6 is it's an angle that I'm probably going to know the cosine value off the top of my head. And it lies between 0 and pi over 4. That's the motivation there. So when I plug this in, it's going to be, well, I'm going to plug it in right there. And actually, if I plug in pi over 6, I probably should have plugged in pi over 12. But it just so happens, turns out that pi over 6 times 2 is pi over 3, and I know that's a nice angle as well. So we're going to look at the cosine of pi over 3. Well, pi over 3 is a 60-degree angle, and the cosine of that is positive, right? It's positive half probably or something. It's positive. And then this turns around and makes it negative. Multiplying by 4 doesn't change the sign, so this is a negative answer, which means we are concave down. Yikes, I misspelled down. On 0 to pi over 4. And then now we need to try something between pi over 4 and 3 pi over 4. I guess pi over 2 is a nice one. So if I plug in pi over 2, you multiply by 2, and that makes pi. Well, the cosine of pi is negative. Pi is right over there. Its cosine's negative 1. But then you multiply by negative, which makes it positive again. So we are actually positive, which is concave up on pi over 4 to 3 pi over 4. Okay. And again, I chose pi over 2 because it just sits nice in that interval. And I was banking on knowing the cosine of that off the top of my head. And let's see here. Now we just need to pick something between 3 pi over 4 and 2 pi. So I think pi is a good one. And let's see, cosine of pi is negative, but then you multiply by the negative. Oh, wait, I'm sorry. You have to multiply that by 2. So the cosine of 2 pi, right, it's 2 times x. So we really want 2 pi, which is positive. But then you multiply by negative and it turns negative. So it's going to be a negative, which means we are concave down. Remember sad guy, happy guy. This is sad guy. Concave down on 3 pi over 4 to 2 pi. I wrote that like it was going to be a fraction. 2 pi. There we go. Cool. And so now we just need to see, okay, well, where did these guys sit in these intervals? 7 pi over 12. Let's see, that is between pi over 4 and 3 pi over 4, so that's on the concave up, and if it's concave up, let's draw it. Happy guy. 7 pi over 12 must be a minimum. It must sit at the very bottom. So we have a relative minimum at 7 pi over 12 equals x. Probably should put that first, but whatever. And also 11 pi, well, that's on that last one, so that must be a relative maximum. Again, think about it, sad guy, that's a maximum. Now you also have to remember that, this is a periodic function, and so you could always add 2 pi to this, and it's going to kind of circle back around. Actually, let me correct myself. Look at the original function. Because of this coefficient here, the periodic, it's going to be cycling through its period twice as quick. So actually, you only need to add pi to that. So if I wanted to find another minimum, I would just have to add, let's just say, I don't know, k pi for some integer k, and you could also add k pi for some integer there, and you would get other maxes and other minimums. Just don't forget that with cosine and sine and tangent, all those trig functions, they're periodic. So if you want to find all the minimums, all the maximums, you kind of have to add a little stipulation there that you could keep adding, multiples of pi or multiples of 2 pi depending on what the period is. So anyway, so now we have a good example of, we have a couple polynomials, and then we have one non-polynomials. Hopefully this gives you the gist of how this second derivative test is maybe a little bit quicker than the first derivative test, at least in some instances.